говорим о персональном производстве. Но Надя сказала верно, что нужно вспомнить 52-й год и Массачусетский университет. Тогда использовались практически те же самые подходы, которые замотивировали нас на наши достижения. Вот, предположим, ребенок собирает из кубиков какую-то конструкцию. Линейка не нужна, потому что у кубиков правильная геометрия. Это значит, что в этом случае проект не ограничен уже размером машины. Если стандартные блоки, то вы можете их располагать максимально далеко. Но Надя показывала, что есть определенные вещи, которые помогают нам снизить процент ошибок. Например, башня, созданная из таких кубиков, получается точной, функциональной. И ее можно использовать повторно использовать эти элементы. Все эти атрибуты, внутренняя метрология, поправка ошибок, использование разнородных материалов и повторное их использование. Пропал звук. Это гораздо более эффективный способ. И эта идея не нова, эта идея достаточно старая. Ей, этой идее, наверное, 4 миллиарда лет. Это белок, белки в вашем теле. Строительный материал. Кирпичики – это аминокислоты, энзимы, РНК, протеин. Эти разнородные элементы, главное правильно их соединить. Да, со звуком, конечно, проблемы. И фраза «цифровое производство» имеет неформальное значение. Это компьютер и инструмент. Например, фрезеровочный станок. Мы вкладываем код в материал. В историческом контексте, например, телефоны были изначально аналоговые. Сейчас коммуникация осуществляется в цифровом виде. В MIT были заложены основы цифровой коммуникации. Устойчивая основа цифровой коммуникации. Использовались аналоговые телефоны. Раньше, теперь используется интернет для связи, это очевидно. И чем больше пропадает сигнал, очень трудно переводить. Сейчас вы носите в карманах смартфоны, которые имеют очень большую вычислительную мощность. Вы не носите с собой никакие механические устройства для вычислений с шестеренками и так далее. Эволюция цифрового производства поэтому еще не произошла, поскольку вы не носите с собой такие портативные устройства, но она в пути. Мы сейчас проводим исследования в этой области, мы пытаемся работать с материалом. Это может звучать абстрактно, но это также важно, как разница между аналоговым и цифровым телефоном. Аналоговыми вычислительными машинами и цифровыми – это начало новой революции, перехода к персональному производству физических предметов. В этом закладывается глубокое значение цифрового производства. В нашем исследовании мы полагаем, будет несколько этапов. Первый этап – компьютеры, машины. Второй шаг – машины машинам. Третий шаг – код превращается в материалы. Четвертый шаг – программы превращаются в материалы. Наверное, сейчас он предлагает рассмотреть их подробнее. Да, Надя упоминала машины, которые изготавливают машины. Какая здесь основная идея? Эти машины позволяют нам создавать прототипы. Надя показывала Fab. Это был хороший пример. Подход такой. Один человек определяет спецификацию, потом дизайнер работает, потом другой человек превращает это в инструкции, потом это получает оператор, который работает с компьютером. Но когда вы это делаете за один подход, очень плохой звук. Каждый компьютер с драйвером печати используется с разным назначением. Мы создали различные геометрические модули, которые превращают... И в последнее время мы создаем интерфейсы пользователя, веб-интерфейса. Где используется веб-интерфейс. И напротив можно привести еще один пример. Один из наших любимых установок, одна из наших любимых установок. Два из моих студентов создали 3D-модель. Из 3D-модели выработали геометрию. И с помощью того подхода создали что? Отвратительный звук. Очень плохо слышно, к сожалению, докладчик. Это то, что мы сейчас наблюдаем. Это пример микро-лего.
Student now, Will, who's working on automating assemblers for that. And we see that as the successor to 3D printers, are these automated assemblers. it's very hard to print conductors, for example, what we want, but it's very easy to assemble them. What we want to do is recreate the history of electronics down to assembling integrated circuits that way. Here's another example. Kenny Chung is making Lego-like parts, but now these are carbon fiber composites. And so he's linking loops of carbon fiber to make snap-together structures that he's shown are the world's lightest, strongest material. And this is aimed at things like high-performance aerospace, aerostructure. And so we're finding when you make these discretely assembled materials, not only do they have benefits in fabrication, they can have benefits in performance. They can work better than existing materials. So then to make those sorts.
К сожалению, очень тяжело переводить, потому что у меня в наушниках выпадают его отдельные слова из предложений, поэтому не слыша этих слов, трудно расслышать целое предложение, поэтому я вынужден прекратить перевод. Слишком плохое качество звука.
That's the stage where the materials themselves are becoming digital. Then a stage after that is you lose the machines and the materials become programmable. And so we've been studying ways to actually make materials that change shape. Any number of people worked on, this is a workflow that takes a 3D design and turns it into a 1D code, where the 1D code folds into the 3D shape, just like the way protein folding does, but now we get to design it. And so that's, you can think of it as CAM, engineering workflow, but it's an engineering workflow for folding. And we've implemented that over 9 orders of magnitude, from assembling proteins up to robots that fold like mechanical proteins. And perhaps the most ambitious project we're doing with that is when you synthesize DNA today, you do what's called solid phase synthesis. You sequentially wash with bases. Here what we want to do is make a nanoassembler where you wash with geometries, fold, and then you attach nanoclusters of inorganic material so that you actually grow the thing you want to. Instead of printing it, it's a growth process, and you can grow many in parallel. You really machine and you're coding the materials themselves to construct. And so that's how we be getting to fundamentally coding the construction of fabrication. And all told, that's about 20 or so years of research from where we are today to finishing it. Then if you take that research roadmap, interesting historical parallel with the history of computing. There are mainframe computers, and they're analogous to the big expensive manufacturing machines we use. Then there were mini computers. This is Ken Thompson and Dennis Ritchie at Bell Labs inventing Unix. Everything you do today, like email and the internet and playing video games and word processing, came from that period, and that's comparable to the Fab Labs that you've heard about. Then there are hobbyist computers, the Altair, that were inspired a generation but weren't very useful, and those are like these hobbyist machines. And then finally there's the PC, and that's like the personal fabricators we're working on. Now, a 3D printer is not a personal fabricator. A 3D printer can make a piece of plastic. What the PC did was it integrated a number of different elements. In the mini computer, there was a rack for computing, rack for storage, a rack for I/O. There were a whole bunch of different functions. And the PC put them all in one box with easier to use software. In the same sense, in a Fab Lab today, there are additive machines, subtractive machines, big machine, small machine, high resolution, low resolution, electronic, folding, a range of things. And you need all of that to make a complete functional system. becomes a real personal fabricator when one device in one process can make a complete functional system. And that's not yet possible. That's where the research is going. So now to do this work, we in CBA have tools like МИСИСе that let us make one of anything using these very expensive machines. To teach students to use them, I started a class called How to Make Almost Anything, which was aimed at a few research students like Nadia or Alan. But I was amazed when hundreds of students would show up trying to take the class, a response unlike anything I'd seen. And then I was amazed by what they accomplished. So Kelly, the first year, made a device that would save up a scream when you're mad and play it back later. And this was a web browser for parrots. And this was an alarm clock you rest with and convince that you're awake. And this was a dress that would defend your personal space. And these projects happen so consistently. I realized that the students were answering a question I hadn't asked, which is, what is the purpose of digital fabrication? This is Ken Olsen, the head of digital, that commercialized MIT's early transistorized computers that really created the internet. And he said there's no reason to have a computer in the home. DEC is bankrupt to have computers in the home, but they're not there for inventory and theory. They're there to talk to friends, listen to music, do personal things. In the same sense, the students were showing the purpose, the killer app for digital fab is personal fab, and the reason to do personal fab is not to make what you can buy in stores, it's to make what you can buy in stores. It's to make things that match your personal needs, just like you do in computing. And so that in turn led to the Fab Lab project. If we have millions of dollars on campus, if this will all get integrated in the coming years, we put together about $50,000 in equipment, about $20,000 in materials. And all of that together you should think of as sort of one effective machine that lets you make a functional system. And we set up one in Boston, but they spread here to the south of India, coast of Ghana. This is outside Pretoria in South Africa. This is eastern Afghanistan. Every year they've been doubling, about every year and a half they've been doubling, spreading all around the world. We hadn't planned that. So to understand what they are and how they relate, Fab Labs are part of a much bigger maker movement. There's hacker spaces and Make Magazine and Maker Faire and tech shops. There's lots of connections in these projects. They're all expressions of this revolution coming. Within that, one particular aspect of the Fab Labs is the extent they work as a network. All the labs collaborate globally. There's about 150 now. There's a very lightweight set of rights and responsibilities that allow the labs to interrupt. And then there's a core set of abilities, and this is shared across the labs, and that lets people and projects be shared across the lab. This slowly evolves as the technology evolves. So today in Fab Labs, we put in a large format mill that's making like furniture, bicycles, boats, and a growing use for it is making tooling for environmentally friendly composite light strong materials. There's a precision mill for molding and casting and for making circuit boards, a laser cutter for snap fit assembly of 3D structures from 2D parts, a sign cutter for flex circuit printing masks, things like that, a 3D printer, 3D scanner, materials for molding and casting, soft tooling, tools for working with embedded electronics, and engineering and design tools. These are some examples of projects. Again, there's a common misconception that this is about 3D printing. The 3D printer actually ends up being one of the least used tools in the lab. In the top, what I'm showing is in the class at MIT, I a couple weeks ago showed soft tooling. So what the students do is they machine machinable wax, they cast an elastomer, and then in that they cast polymer materials like concrete. And that lets you make a parts that have better surface finish and are stronger, and cheaper. You can make many of them compared to 3D printing. So that's one of the processes. This is an example of snap-together assembly from the laser cutter or using the sign cutter. This is a big monowheel made on the shop block. Using the precision mill, this is examples of electronics made in the lab. Using the large mill, this is an example of composite tooling layup. These are some of the examples of processes using a range of machines in the lab. And you can think about that in powers of 10. My lab has millions of dollars of machines, and the machines cost hundreds of thousands of dollars. The Fab Lab has 10 or so machines, and those machines cost about $10,000, or they all add up to one of the off-campus machines. In turn, with the machines in the Fab Lab, you can make one of these kinds of machines, and they're about $1,000. And a few of those together let you make a functional system. And then just at the edge, with the smaller machines, you can make even smaller machines for hundreds of dollars that don't yet work really well, but are beginning to emerge. And so a Fab Lab for $100,000 costs much more than one of these $10,000 machines. But the crucial distinction is the Fab Lab has everything you need, not just to use the machine, but to make the machine, to make the machines themselves. So think of it as kind of the scale of what you'd expect in a town library in a community scale. And instead of the cost just coming down, what we're finding is each of these levels is getting populated. You could use one of these at home, you could use one of these in school, you could use one of these in a community resource, you could use one of these at a place like MIT or МИСИСе, and they each participate in the flow of capabilities. So then as the Fab Lab spread around the world, I had thought the research was the future, but people started doing things today, just like in the early days of computing. So now I'll take you on a tour to see some of the labs. This is the VAG lab in Amsterdam, the old customs house. A fun project they did is they made a custom foosball table, where in the lab they designed the table. They did soft tooling for molding and casting to cast the characters. This was David playing Darth Vader and made the electronics to keep score. This is a wonderful lab at an arts colony in Maine. This was used to make tooling for glass or custom printing plates, things like that. They're not designing on the computer, they're using the lab to work in materials they otherwise use. This is a composite boat that Nadia helped make at the Haystack Lab, making the tooling and then laying the frame for that. This is a lab in Tulsa in collaboration with Spirit Airframe Company. They have trouble finding people. They can find people with degrees but not skills. One of their interests was people really learning how to make things usefully. And one of the projects there is working on UAVs, flying vehicles that you could make in the lab. There's a wonderful lab at a series of community colleges in the Midwest in the US in what's called the Rust Belt, where old industry left, that's training a new generation for a new kind of industry. This is a lab in Detroit, and one of its main services is a social service. It takes at-risk youth, kids in the juvenile justice system, teaches them digital fabrication. Through that, they learn about science and technology, engage in society. and have better outcomes than the other kind of social services that we're working with them. There's a very interesting connection between these labs and civic planning. So I was recently in Toulouse, where this is the front of the lab, but this is the back of the lab. There's a big abandoned industrial warehouse the city didn't know what to do with. It has more space than I think any other lab I've seen. And they're using that now as a community resource for a Fab lab. We helped South Africa's government set up a network of labs. This is the one in Soshangovi. They had programs in a number of different areas that weren't working that well. Instead, this is an investment in infrastructure that's similar in spirit, but now happening on a much larger scale in Russia. With МИСИСе, we're collaborating on creating a reference lab that'll help support a network of what looks like maybe 100 or so labs coming across Russia. This is a lab in Manchester, England, and they used to have almost all of the world's mills in the Industrial Revolution. Now industry is left there. And so they're working on new kinds of businesses where you can come to the lab and design something, and you ship data to go to market, then it gets produced on demand around the world. So really building a notion of a new kind of industry that's not based on owning factories. It's based on doing production on demand at sites all around the world. This is a lab in Afghanistan. One of the projects there made community internet. And from there, the internet produced there is the same project is running commercially based out of a lab in Kenya. This is a wonderful project at a lab in Barcelona that made a complete solar house, a rapid prototyping project. And the people there are actually running the city, believe it or not. They ran for and won the last election, and the connection is there's 50% youth unemployment, but they still buy products maybe far away. So they want to be globally connected for knowledge, but self-sufficiently locally, technically, for what, so skills and jobs are local, and so they're deploying the labs as part of the infrastructure of the city, as part of their city planning. This was a lab at the World Economic Forum. This is one in Washington, D.C. At the end of the street is the Capitol building, but it's in a poor mixed-use neighborhood. And projects like this led to very interesting legislation. This is President Obama visiting one of these labs, proposing to turn these into a new national lab. Our national labs, like yours, are very expensive and aren't very successful at impacting the communities around them. And so as a complement, this is looking at the network of national labs as a new kind of network of community labs as a kind of national lab. And so as this has grown, we've had to build new organizations to keep up. There's a series of meetings that have spread around the world. This summer we were in New Zealand. The next one is going to be in Japan, in Barcelona the year after that. Up with this, now spinning off is a foundation that links regional programs for operational support, funds for business investment, and then I want to talk about the educational piece. This is Hans Christian from the lab in the far north of Norway. This is a robot truck designed and made in the lab. This is Chapiso from Soshangovi. She was using the lab to follow my classes at MIT. We had a problem that kids were getting skills so far advanced of local opportunity. The usual response would be to tell them, you have to leave now and go our way. But in the labs, they have tools and they have the global connectivity. So we started what's called the Fab Academy, and it does distributed education. Students have peers in work groups in the labs that are then linked by broadband video, like we're doing now, and online content sharing. And you can think about this, again, in a computing parallel, if you go back to the history of computing, MIT is sort of like a mainframe. You go to MIT for processing, and we can fit a few thousand people. There's a lot of attention now to open courseware and things like that, online distance learning. But that's like time sharing. You're like a terminal connected at a distance to the mainframe. And you can think about this Fab Academy as more like the internet, the network of sites. There isn't a central site and spoke coming out. Instead, students have peers and groups in the lab who are then linked globally. And the deep connection between fabrication and education is digital communication lets us talk to each other. Digital computing lets us share designs. With digital fabrication, the campus can come to you. So I could design something in my lab here, and if I made, this is a project I'm working on now. If I made that project, I could send it to you, and you could make it there and work on it and send it to me. And so the campus itself can travel in the network, and it lets you make this distributed educational model that we believe will be much more scalable. And so right now there's only one class in the Fab Academy, Principles and Applications of Digital Fabrication. But in the coming years, we expect this is going to grow into a whole sequence for advanced research and education that's fundamentally distributed, and in that way much more scalable and tapping a much greater fraction of the world's brain power. So with that, there's background. Oh yeah, I'll end with this note. This is Seymour Papert, who was a pioneer in first connecting kids to computers. And you can really trace Windows and mice and all of that to work that came from this period. And when he saw Fab Labs emerging, he had this very interesting comment that he, rather than being unrelated, he saw them as a fulfillment of the arc from the beginning. Because from the beginning, the goal was not just for kids to tell what computers were to do, he wanted the kids to actually create the technology. And that's what we're finally able to do now in this period of Fab Labs. So there's background on the CBA site in this Fab book. There's a recent article in Foreign Affairs if you want to read more. But and then you've got great resources for the project with you in person. And so by joining the Fab Lab network, you're surfing this research roadmap towards digital fabrication. You're joining this network of hundreds of sites around the world that are collaborating on technology and the impact and the education. And rather than thinking about it, is it education, is it business, is it outreach, think about it as a slice across all of them. A little bit like, if you look, for example, at Kendall Square around MIT, it's a cluster that does research, education, play, art, business, all of that. And the Fab Labs are doing that in the same sense on a local scale, but linked globally. So with that, I'll thank you and be happy to take questions.